Adversaries are currently executing a strategy known as harvest now, decrypt later. Across global network interconnects, encrypted traffic is being continuously duplicated, siphoned off, and stockpiled in massive data centers. The targets are specific. Attackers are hoarding data with a long shelf life: financial ledgers, healthcare records, government communications, and critical infrastructure blueprints. They are storing this data for a specific moment in the future, known as Q-Day. This is the point when a cryptographically relevant quantum computer, a CRQC, comes online with enough processing power to break traditional encryption algorithms. The threat isn't waiting for the hardware to be built. The vulnerability window is open right now, because the encrypted packets captured today will sit patiently on storage drives until that processing power arrives to unlock them. Waiting for a functional quantum computer to exist before upgrading network security guarantees the retroactive exposure of every piece of mission-critical data currently in transit. A common industry assumption is that quantum computers will uniformly shatter every existing form of network encryption. In reality, the mathematical impact is highly selective. We have to divide our cryptographic models into two distinct categories: asymmetric math, used for keys and signatures, and symmetric algorithms, used for bulk data encryption. Asymmetric algorithms, specifically RSA and elliptic curve cryptography, rely on mathematical factoring. Quantum computers excel at this specific problem, meaning the protocols we use for key exchanges and digital signatures are highly vulnerable. Symmetric algorithms like AES 256 operate differently. They require brute force attacks to crack. A sufficiently long symmetric key remains computationally secure against quantum processing. The immediate industry response is the standardization of new post-quantum cryptography algorithms, such as ML-Chem and ML-DSA. These are designed specifically to replace the vulnerable asymmetric key exchanges. Swapping out key exchange algorithms at the application layer is insufficient. Securing a service provider backbone requires a transport architecture that applies line-rate symmetric encryption at the hardware level. A rigorous quantum-safe architecture uses new PQC protocols to safely establish keys, while relying on robust AES 256 to protect the actual payload in transit. At the boundaries of any service provider backbone sit the provider edge, or PE, routers. They act as the gatekeepers for secure transport. Before a single packet of sensitive payload can be transmitted, these edge routers must securely agree on encryption parameters across a wide area network that we assume is already compromised by listeners. This happens in the control plane through the MACsec Key Agreement, or MKA, protocol. The two PE routers initiate a background handshake to establish a shared secret. From that shared secret, they derive the Secure Association Key, or SAK. To protect against quantum interception, this derivation uses a hybrid of standard AES 256 and new PQC algorithms. This handshake happens entirely out of band, strictly separate from customer data flows. This hybrid MKA handshake ensures a mathematically quantum-proof parameter is locked in before user payload ever hits the wire. Once the secure parameters are set, we shift from the control plane to the data plane, looking at the exact moment the first packet of customer data arrives at the ingress router. Nokia addresses this with an in-network encryption mechanism called AnySec. Instead of relying on external appliances, AnySec is powered directly by the MACsec hardware encryption engine built into the router's silicon. Let's examine the anatomical transformation of the packet during AnySec encapsulation. A standard data packet consists of routing labels, headers, and the user payload. The AnySec engine isolates the payload section and uses the previously established SAK to convert customer data into unreadable ciphertext. The MPLS routing labels remain outside the encrypted zone, clearly visible and unaltered. This selective, hardware-driven encapsulation achieves data obfuscation without destroying the routing instructions the network needs to function. We can track this newly encapsulated packet as it leaves the edge and enters the high-speed core network. In the core, the intermediate provider routers, or P routers, handle the traffic. They are programmed to read only the outer MPLS labels to determine where the packet needs to go. Because those labels were left untouched by AnySec, the forwarding behavior of the P routers remains completely standard. The core network requires 0 new protocols to handle the encrypted payload passing through it. Since the hardware encryption is native and bypasses complex software tunnels, the traffic maintains strict line rate speed with no latency penalty. The core network operators and any potential wiretappers are rendered blind to the payload, neutralizing inside threats while preserving raw transport speed. Historically, engineers have relied on overlay networks like IPsec to encrypt traffic across untrusted domains. We have to evaluate the structural difference between building an overlay network and utilizing native in-network transport encryption. The IPsec model places a box around the pipe, stacking multiple IPsec headers onto a packet. This creates significant encapsulation complexity. The AnySec model puts the lock inside the pipe. It integrates directly into the native MPLS backbone, securing the data without requiring additional bulky tunnel headers. IPsec provides flexibility when routing over the public internet. However, applying that overlay to a dedicated backbone imposes a severe computational and bandwidth tax. For service providers operating their own core MPLS networks, native AnySec encryption is the viable path to achieving quantum safety without crippling network performance. Transport security forms a specific component within a broader, multi-layered defense in-depth strategy. This chart details the architecture for quantum resilience. At the base, the key management layer uses AES encryption to distribute keys. Moving up, AnySec encryption secures the IP and MPLS data plane, supported by MACsec at the Ethernet layer and QKD at the optical layer. True quantum-safe connectivity is built by integrating a unified, multi-layered cryptographic defense from the physical fiber straight up to the application layer. The Harvest Now threat actively exploits the gap between the asymmetric cryptography we use today and the inevitable arrival of cryptographically relevant quantum computers. Decoupling payload encryption from routing labels via hardware-level symmetric encryption effectively neutralizes this vulnerability. By redesigning the transport architecture now, network engineers can future-proof mission-critical data without sacrificing the line rate performance their core infrastructure depends on.